Welcome to the RIS 101 webinar. This is a non-technical introduction to the Renewable Integration Study, or RIS for short. This is intended as an introductory webinar where the concepts explored in the RIS are explained. This is part of a 5-part series of webinars on the RIS. In later episodes, we'll delve further into the technical detail, our action plan to transition the industry, and the 3 technical appendices. To read the RIS publications or view the other webinars in the series, check out the AEMO website. Presenting this webinar today is myself, Eloise Taylor, and my colleague, Jane Yu. We are both members of the Future Energy System team at the AEMO, and we have both been working closely with the technical RIS studies over the past year. So, a bit of background on who we are as a company. The Australian Energy Market Operator, or AEMO, is the independent system and market operator for the national electricity market and the Western Australian wholesale electricity market. We also operate retail and wholesale gas markets across the southeastern Australia and Victoria's gas pipeline grid. AEMO is owned 40% by market participants and 60% by the governments of Australia. In the last financial year, we traded 213 terawatt hours of electricity, which is valued at more than 20 billion Australian dollars. Today's webinar is focused on the national electricity market, which operates on the east coast of Australia. In today's webinar, we will be looking at why AEMO is planning for change in the electricity industry, the focus areas the RIS studied, and the high-level outcomes of the RIS. I'll now hand over to my colleague Jane to continue the webinar.
Thanks, Elle. So let's get started with an overview of how the energy landscape in Australia is changing and why AEMO needs to plan for this. Focusing on the national electricity market on the eastern coast of Australia, we will look at what has been happening, what will happen, and how that will impact us. Currently, the national electricity market is experiencing similar penetrations of wind and solar to many other countries around the world. Now, it's important to understand that there are many ways of looking at penetration. Often, you'll find that it is described as how much energy over a whole year might have come from wind and solar, which is the orange bar we have here. Now, electricity is transferred at about the speed of light. So when a ray of sunshine hits a panel or a gust of wind blows a turbine, the energy is consumed at that very same instant. Perhaps the gust of wind blowing a turbine down in South Australia powers someone's TV while they are watching Netflix up in Queensland. So where there is a demand for electricity, the supply for electricity must occur in the same instant. This is what the Renewable Integration Study looks at. It looks at how much energy at any single point in time might be coming from wind or solar. This is the instantaneous penetration, represented by the red bar. What you are seeing on your screen is a comparison between Australia and Texas in 2018. What we can see is that in 2018, we weren't too far behind Texas in terms of our wind and solar penetrations. It is worth noting that we actually looked at a whole lot of power systems around the world and compared them to ours. For some, we are not far behind. For some, we are on par. And in other areas, we are world leading. This information can be found on our website. The more we delved into how other countries around the world got to where they are today, the more we learn how unique the national electricity market in Australia is. For example, take a look at the lines on Texas and then the lines on the east coast of Australia. Our power system is long and skinny. Compare this to Texas and a lot of other power systems, which have more lines connected into one another in a small space. The different topology of the networks mean they respond differently to high penetrations of wind and solar. So even though the numbers might look similar, and there are many things to learn from other systems, we still need to manage an inherently different network. Further, if we were then to compare the numbers for each state on the east coast, we can see that some parts of Australia are very much beyond international penetration levels. This makes us where the world needs to learn from most. And if we are like this already today, Looking forward to 2025, we're expecting an extra 50 to 100% more wind and solar to be installed. This includes a doubling of the current capacity of distributed solar PV installations and means that across the whole East Coast, we could reach instantaneous levels of available wind and solar energy of between 75 to 100% of the electricity demand. At a system-wide level, this is going to be a huge and rapid change. If we flesh out the change a little bit more, looking at every half-hour instant in a whole year, we can compare where 2019 was to two different 2025 scenarios. The central scenario, based on current policies and market reforms, and the step change scenario, which assumes aggressive decarbonisation. In 2019, the largest actual instantaneous penetration we saw was just under 50% at any one time. Because this is what actually happened, you can expect it to incorporate everything happening on that system during that point in time. This might have been a bushfire cutting off some lines connecting generation. In contrast, because 2025 is in the future, the numbers are not limited by these additional things. So view them as what the physical built system is capable of reaching. And we can see, with all the new things that are going to be built, 2025 is going to show much higher levels of instantaneous penetration. The central scenario can reach 75% and beyond at any instant in time, while the step change shows we can harness the value of Australia's natural resources to cover 100% of the demand at some instances in time. This is what we need to prepare for. So AEMO's role in this is to help ensure that Australian consumers, businesses and industry have access to secure and reliable energy at all times. What this means in practice is that we need to make sure that electricity is available and can get to everyone safely and when we need it. So when we have a large and complicated system that is engineered to ensure that you have access to safe and high quality electricity exactly when you need it, we have to keep the system operating smoothly. And there are a number of physical properties, also called power system characteristics, that AEMO needs to help keep in check, including the balance of supply and demand of electricity, managing uncertainty and variability, managing frequency, and monitoring system strength and voltage levels. We'll look at these concepts further in the following slides. If those properties are not kept in check, electricity may become unsafe to use, or a large amount of people may temporarily lose this power. You might also notice strange things, like your solar panels tripping off, or lights flickering, or fuse switches blowing. And now I'll hand back to Al to talk a little bit more about the things that we studied.
Thanks, Jane. So now we understand a bit more about what AEMO does and the increasing levels of wind and solar in Australia. Now we can start to look at the different physical areas that are undergoing change through the increases in wind and solar, what these all mean, and why we should care. These are the areas that we studied in the RIS. So in order to fully understand the physical properties that AEMO needs to keep in check and why these properties are changing, we need to go back and understand the differences between the technology we've used for over 100 years and the technology we are going to be using in the future. So the first key change that we need to understand is a change in location. Traditional generators were large. They were built in specific, known locations, and there were relatively few of them that needed to be coordinated in order to make sure that the right amount of electricity was being generated to meet demand at every point in time. On the other hand, wind and solar, particularly solar, can be installed on relatively small sites, like on any home in any street in Australia. This means we have millions of small, decentralized generators dotted everywhere. These are largely invisible to AEMO, and we cannot coordinate them like we do the large-scale generators. So, what is distributed PV? Well, the type you may be most familiar with are the solar panels on your roof. However, distributed PV encompasses all residential, commercial, and industrial solar power systems, which AEMO does not have visibility over or controllability of, like we do with other large generators. The amount of distributed PV across Australia is increasing at a very rapid rate. Even today, if considered collectively, all the distributed PV across the national electricity market would be the largest generator in our system. By 2025, the size of all distributed PV considered together could be more than 26 times larger than our current largest coal generator on the grid. Distributed PV is effectively a very large generator, in fact, the largest generator, and growing. And AEMO cannot see it. We do not know for certain how much electricity this largest generator will produce at any given time. We can guess, but we do not know. This makes it increasingly difficult to balance supply and demand. Remember, balancing supply and demand at every moment is very important to making sure energy travels safely to you when you need it. Further, your rooftop system is probably going to be different to that installed 2 streets down from you, which means they have varying capabilities, both good and bad. These varying capabilities make it even harder for AEMO to ensure supply and demand are balanced and to ensure that the system is secure. Given this is such a rich resource and an integral part to consumers' lives, increasing the good capabilities, increasing visibility, and increasing controllability of distributed PV will help unlock the value they bring to consumers and to the network. While the ability to control rooftop solar output might seem dramatic, it would likely happen only rarely and at times of traditionally low demand, such as spring, autumn, and weekends. This is a better option than having to limit new installations or having arbitrary output limitations that impose export limits all year long, even at times when such limits are not necessary. The second key change is a change in energy source. The sources of energy from conventional generation are what we call firm. They are largely constant. For example, you can store water in a dam to run a hydropower generator, and you can stockpile coal or gas to run a coal or gas generator. For wind and solar generators, the availability of their fuel is not constant. It's variable. When the sun is shining, the solar farm can generate, and when the wind is blowing, the wind farm can generate. Variability is the movement up and down in demand or resource availability. Importantly, these movements can come from anywhere, not just large-scale wind and solar and distributed PV. For example, demand moves in a daily cycle. It increases when everybody gets up in the morning, then it increases some more when everyone gets home from work and does their evening activities. Then it decreases when we all go to sleep overnight. Wind and solar, however, have added variability because of their weather-based nature. And this variability is increasing as the amount of large-scale wind and solar farms and distributed PV is also increasing. Looking at the figure of the large-scale solar generation over a day, we can see that there is some variability that we can predict really well and other variability that we cannot predict well at all. How well we can predict how much supply or demand there will be at any point in time is called the level of uncertainty. So, for this large-scale solar farm we see here, it increased its generation as the sun rose and decreased its generation when the sun set. The daily sun cycle is easy to predict. The figure shows the purple forecast line is close to the red line, which shows what actually happened. So in the morning and in the evening, these two lines are quite close. However, this was a cloudy day, and cloud movements are less easy to predict. The figure shows that at times through the middle of the day, the actual generation, the red line, dropped to be up to 66% lower than what we thought it was going to be, the purple line. The graph also shows that the generation moved up and down a lot more than expected. So it was both more variable and more uncertain. As you can imagine, Not knowing with a high degree of certainty how much wind and solar generation can be supplied will make it difficult to keep supply and demand balanced at all times. As the amount of large-scale wind and solar and distributed PV increases, this balancing becomes even harder. So to ensure that we have enough supply, enough resources available to be able to meet demand when you need it, we need to know what all the resources available are and when they'll be available. If there is a large cloud that passes over Brisbane and everyone's rooftop solar cannot generate for even a minute or two, or there's a sudden decrease in wind speed that was previously blowing through all the turbines near Adelaide, we need to know that there is another generator ready to pick up that slack. However, if supply and demand get too far out of balance and there isn't another generator to pick up the slack in time, some of the demand might need to be reduced, and this is called controlled load shedding. I'll now pass back to Jane to go over our final key change.
Thanks, Al. So, the final key change is a change in technology, where conventional generation that we have been using for the last 100 years in the form of large spinning thermal and hydro plants were governed by physics, produced this purple waveform that we have here. Wind and solar need an inverter to change, for example, the straight line of power from solar panels into a wave. This is why you need that device called an inverter that comes with the solar panels on your roof. The waveform is important because this is what all the devices in your house and all the poles and wires on the network are expected to work on. If the waveform isn't smooth, then we can start getting an unstable system. How often the waveform repeats itself is measured as frequency. Like the heartbeat of the system, everything follows frequency. The conventional machines, through their natural physical spin, which is why they are called synchronous, and wind and solar through the inverter. Frequency makes sure the system is working together all the time. When we look at the value of frequency, we can find out how balanced supply and demand in the system is. In Australia, we expect a completely balanced system to be at 50 Hz, repeating 50 times per second. If we suddenly lose a generator, perhaps due to a lightning strike or a bushfire, we get this kind of imbalance, which we can think of on the scale as the demand side getting heavier and outweighing the supply. As a result, the frequency dial in the middle shows the frequency dropping. Now, because all the devices in your house and all the poles and wires on the network expect a nice waveform at 50 Hz, if this imbalance happens too fast or the frequency goes into the red zone, they can be damaged. This is why we need frequency control services that can manage how quickly frequency changes and ensure it stays within safe boundaries. Now, that's always been the case even when we had lots of conventional generation. Nowadays, though, there's more to it. Amongst all the devices in your house and on the network, there's a new one, the inverter, that came with the solar panels on your roof and the big wind farms and solar farms on the grid. Inverters are like little computers that can have all kinds of things programmed into them, including protection. When they sense the frequency is changing in a way that doesn't make sense to them, they might switch off. So if we go back to the balancing scales, we lose this coal unit, frequency drops, inverters don't really like that, so they also disconnect from the grid. This means the demand side of the scale gets even heavier, to a point where if the imbalance gets really bad, some of the demand might need to reduce to avoid the system switching off. In addition to frequency, there's another system characteristic that is important for being able to maintain and control the waveform. This is known as system strength. Like frequency control services, system strength comes from conventional spinning machines. The network is stronger where and when we have more conventional generation online, and the network is better connected together. However, where the network is strong may not necessarily be where the best sun shines or the best wind blows. A lot of wind and solar is being installed in long and skinny parts of the network, which are weak. In future, As more conventional generation goes offline, the system becomes weaker, which makes it even harder to keep that nice, smooth waveform. This can create all kinds of technical issues for the grid, and therefore the quality of your power supply. This is why we need a minimum level of these spinning machines online to help maintain system strength right now. As a result, this forms a bit of a limit to the amount of wind and solar that can be online, a limit that Australia could be at the forefront of pushing beyond because of our unique, long and stringy network. Now let's hand back to Al so she can talk about the rest of the study.
Thanks, Jane. Now that we've covered the areas that were studied in the Renewable Integration Study, this final section aims to give a quick summary of the findings. If you'd like a deeper dive into any of the analysis, have a look at the webinars on the Renewable Integration Study technical appendices on the AEMO website. For now, let's return to the same scatterplot that we had at the start of the webinar. As a reminder, each of these dots represents the proportion of demand being supplied by wind and solar at each half-hour mark in the year. The first key finding from the study was that we start seeing some of the impacts of the changes mentioned in the previous sections at wind and solar penetrations above 25%. So anywhere in the yellow region here, which means even today we must manage some of these issues to ensure consumers are getting their power safely, exactly when they need it. As we start seeing more and more half-hour dots entering this yellow region in 2025, the work needed to manage these issues will increase. As an outcome of the Renewable Integration Study, there is an action plan to help us push further into this yellow zone and get to 75% at any point in time. Remember, this 75% is an instant penetration at a single point in time and not a yearly average. If the actions are not taken to manage distributed PV, variability uncertainty, frequency, and system strength, wind and solar might have to be limited to help manage the issues and challenges we are seeing. The 75% mark, where the dark line is where we can currently make it to with the technologies and systems available to manage frequency and system strength. In the future, as these technologies mature, it will be increasingly possible to go beyond the grey zone towards 100% at any one time. As part of AEMO's role, we need to ensure you have safe, reliable electricity exactly when you need it. We need to ensure that now and into the future. The Renewable Integration Study has set out an action plan to manage the significant transformation in the next 5 years. This would allow a potential 75% of our energy to come from wind and solar at any instant in time by 2025. The next steps to take are an analysis on costing to ensure that we are maximising the benefits to end consumers. This analysis, alongside developing a blueprint for the strategic construction of the network to transport energy to consumers, is ongoing as part of AEMO's integrated system plan. As the physical system changes, the market and rules that govern this system will also need to change and be flexible to adapt to any future changes beyond 2025. This is important to keep in mind going forward as we keep pushing the internationally leading levels of renewables and become a world leader in demonstrating the successful operation of a large power system with high levels of wind and solar. Thanks for watching the RIS 101 webinar today. For a more detailed technical overview on the study, including details on the RIS action plan or a deep dive into the 3 RIS appendices, head to the AEMO website to check out the rest of the series.